Similar to how meteorologists fly into hurricanes, NASA has now flown a mission through the heart of a magnetic reconnection explosion. We call this mission MMS. This team of 4 spacecraft studies magnetic reconnection, powerful explosions that occur when magnetic fields collide and realign, a process that occurs regularly throughout space. Close to Earth, and throughout the universe, space is far from empty. It contains electrons and ions, and most importantly, magnetic fields. This dynamic environment is unlike anything we experience on the ground. As we rely more on satellites, or even prepare for a journey to Mars, we need to understand this complex system. Magnetic reconnection is one of the key forces driving particles to accelerate through space, and it's a fundamental driver of space radiation, a critical phenomenon to understand when protecting our satellites and astronauts. On October 16, 2015, MMS traveled straight through a magnetic reconnection event at the boundary where Earth's magnetic fields bump up against the Sun's magnetic fields. In only a few seconds, MMS collected hundreds of observations of the way the magnetic fields and particles were moving, represented with arrows in this visualization. Watch how they go along steadily and then suddenly begin to go in every direction. This is the point where the magnetic fields reconfigured and particles were sent racing off at high speed. For the first time, we have observations from the epicenter of an energy transfer as important to how things move in space as gravity is to how things move on Earth. This is just the start. In its first year, MMS made more than 4,000 trips through the magnetic boundaries around Earth, each time gathering information about the way the magnetic fields and particles move and interact in our space environment. Crucial information as we make plans to explore far beyond our home planet.
Out in space, particles play by a different set of rules than we are familiar with at home. The expanse beyond Earth is almost entirely filled with a mysterious state of matter. This matter is the least understood. It's rarely encountered on Earth, yet it triggers auroras and even impacts our exploration of space. This is plasma. After solid, liquid, and gas, plasma is the 4th state of matter. It is made of particles that have been ionized. This means the particles have been given so much energy that electrons separate from their atoms, making a subatomic soup. Unlike gas, plasma easily conducts electricity. This allows it to move along invisible pathways charted by the electromagnetic fields that fill space. While plasma is rare on Earth, it makes up 99.9% of the visible universe, including the Sun and other stars. It's also spread out across the universe and the space separating planets and stars. This space is not empty, it's filled with a weak soup of plasma. Those vast expanses of space are also filled with electromagnetic fields, such as those created by the Sun and Earth. In these places where plasma and electromagnetic fields play, plasma can undergo a unique explosive phenomenon called magnetic reconnection. Magnetic reconnection occurs where magnetic field lines are constantly shifting. When the lines become tangled, they explosively snap and realign. This transfers energy and sends nearby plasma particles flying through space. Magnetic reconnection triggers solar flares on the surface of the Sun, creates shock waves near supernovae, and violently twists plasma around black holes. Closer to home, magnetic reconnection between the Sun and Earth's magnetic fields is a critical way energy is transferred around our planet. For example, when magnetic reconnection occurs on the night side of Earth, it can push particles down toward the poles, triggering auroras. Near-Earth space is the easiest place to study magnetic reconnection, and NASA does this with its Magnetospheric Multi-Scale Mission, or MMS. MMS uses 4 identical spacecraft to measure magnetic fields and particles in 3D 100 times faster than previous missions. This has revealed new insights on the small-scale details of magnetic reconnection and the nature of plasma itself. Other NASA missions like Parker's Solar Probe, Themis Artemis, and Voyager also study plasma across our solar system. From the surface of the Sun to the space between the planets, NASA continues to unravel the mysteries of plasma that help us as we venture beyond Earth.
Throughout the universe, there are forces fundamental to how things move. Just as gravity is key to how things move on Earth, a process called magnetic reconnection is key to how charged particles speed through space. The more we understand how those particles are accelerated, the better we can protect our spacecraft and astronauts as we explore deeper into the solar system. And now, NASA's Magnetospheric Multiscale Spacecraft, or MMS, has discovered magnetic reconnection occurring in a new and surprising way near Earth. Typically, images of our planet from space show a blue-green sphere engulfed by the darkness of space. But invisible to the eye, a vast network of magnetic energy and particles surround our planet. Earth's magnetic field creates a protective bubble that shields us from highly energetic particles that stream in both from the sun and interstellar space. As the solar wind bathes our planet, Earth's magnetic field lines absorbs this energy and gets stretched. And like elastic bands, they eventually release energy by snapping. As a result, particles in the region are flying at supersonic speeds. That burst of energy is magnetic reconnection. It's pervasive in the universe. It happens on the sun, around Earth, and flings particles across the solar system. Scientists have observed this phenomenon many times in the magnetosphere, Earth's vast magnetic environment. Now, in a new study, MMS caught the process occurring in a new region. For the first time, magnetic reconnection was detected in the turbulent magnetosheath, the boundary between the magnetosphere and solar wind. This region is made up of turbulent plasma. It's one of the most chaotic regions in the near-Earth space. MMS captured 3D observations by flying 4 identical spacecraft in a tight pyramid formation through the magnetosheath. These arrows show the hundreds of observations MMS took to measure the changes in particles and the magnetic field. This is the moment MMS sees bursts of energy from magnetic reconnection. But these signatures don't look like standard reconnection. Compared to standard reconnection that occurs over tens of thousands of miles, this new magnetic reconnection spans only a couple of miles within turbulent plasma. These reactions are essentially much smaller but more stretchy elastic bands that accelerate particles 40 times faster. In short, MMS spotted a completely new magnetic mechanism that's much quicker than we've seen before. Just like when you mix milk into coffee, turbulent plasma in space moves randomly and creates vortices. It can transport particles and energy, but a lot is unknown about how these particles move through these regions. Showing that this new magnetic reconnection plays a role in turbulent plasma gives scientists insights into how turbulence influences particles moving through space. By looking at such fundamental processes in space at both large and small scales, scientists can learn what drives the complex environments we travel through to explore our solar system and beyond.
There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.